starting with the Coulomb scale to spin orbit coupling and crystal electric field. The net spin of the electrons sitting on the rare earth sites gets divided up into these crystal electric field multiplets, and which are split by some scale, and often the magnetism is the low temperature magnetism is captured by this lowest doublet, which is the effective spin half. And once we think about these rare earth pyrochlores, we usually think about the magnetism coming from this lowest energy doublet. For these spin half doublets, one then tries to write down spin Hamiltonians, like in the simple classical case, nearest neighbor Ising Hamiltonian, and then one tries to understand their properties, particularly because this is a corner shading geometry. As many of you know, this interaction can be written as the total of the spin per tetrahedron, and because the ground states are macroscopically degenerate, and all you want is that the total spin in each tetrahedron adds up to 0, and that goes by the famous name, the ice rules, the 2 in 2 out rules, which basically is in a disguised form a Gauss's law, where you can think about drawing a surface around this tetrahedron and think about a fictitious magnetic field such that the spins, that the total flux of this magnetic field in this 2 in 2 out configuration is 0, and that this dipole. So this Gauss's law has immediate consequence in the sense that even though the system is not ordered, we have power law spin correlations, to be precise dipolar spin correlations, which have been observed in experiments in more than one compound. This is for holmium titanate. Okay, so this part is very well known, and there have been works over the years. Oh, by the way, once you violate the Gauss's law, you get excitations which are similar to magnetic monopoles, and the low energy physics is often captured by the dynamics of these magnetic monopoles. But what I want to tell you about is this. There are certain class of materials like the terbium titanate, etc., where the difference between the lowest doublet and the next doublet is not that large. In this case, only about 17 Kelvin. So to describe the low energy physics, you need to keep track of both these doublets, and so you have 4 states. In other words, you have a spin 3/2 representation, which is the right thing to do, use to capture the low energy magnetic physics of these systems. So then one uses a Hamiltonian which has an on-site term which describes the splitting between these 2 states. The upper state you can take plus minus 3/2, and the lower states plus minus 1/2. It really doesn't matter which one is called which, but you have a on-site term which separates these 2. This is the crystal field energy cost, and then you can write down the symmetry allowed spin Hamiltonian for this spin 3/2. What I'll tell you about is a simplified story about when you take the simplest possible Hamiltonian or an 3/2 Ising model, nearest neighbor, on this keeping all the 4 states. Okay, so this is the thing that I'll consider, which I'll call classical spin 3/2 Is. It has the on-site term that splits the 2 doublets, and then there is a nearest neighbor Ising Hamiltonian. Okay, so one can again go through the same exercise. One can, since this is a corner shading geometry, one can write it in terms of the total spin out of a tetrahedron. But now, since SZ square is not a constant, it renormalizes this on-site term, and this is the point that when the spin exchange and the crystal field splitting are of the same order, then both these energy scales become important, and this leads to more interesting physics than regular spin ice. Okay, so if you do given that there are two energy scales, the first one controls the crystal field excitations, and the second one controls the magnetic monopoles. One finds that when the crystal field excitations dominate, one gets the regular spin ice. 1 and 1 bar basically is a shorthand for half and minus half, and 3 and 3 bar are shorthands for plus minus 3 half. So when they are when delta is greater than JZZ, you get the regular spin ice. When delta is much less than JZZ, you get the what is called an inverted spin ice, but for all practical purposes it's the same thing. The interesting region is here, where you these two terms compete and you get new things. Okay, so let's yeah, so this is what I just pointed out. So what happens when you this energy scale vanishes is that you get a enhanced degeneracy with larger Pauling the entropy at the ground state, and this controls a lot of physics in the low energy at low temperatures in this small region on both sides of this special line. Okay, so let's first start with this part where this delta X energy scale, the crystal field energy scale, is slightly bigger than the exchange scale. So in particular this region, the ground state is the regular spin ice with plus minus half, the total spin of a tetrahedron being 0, but the excited state is not a monopole coming from this term, but this excitation where it just flips one of the sides from plus minus half to plus minus 3 half, maintaining the 0 monopole constraint, and this happens in this energy scale, which is lower than the monopole energy scale in this region, and this leads to new excitations, which is this crystal field excitations. And you can see this when you do a numerical calculation on this. There is a plateau corresponding to this energy scale until before you recover the full spin 3 half entropy. So these excitations being additional excitations than the magnetic monopoles, let's try to ask what are the consequences. Okay, so the first thing that one must realize is that if you create these excitations, okay, so which I'll call as delta excitations, there is no way to get rid of them without creating a monopole. So even though the low energy excitation, they are low energy excitations, they are sort of, to get rid of them, you need to undergo this activation process, and hence these excitations are metastable. So once you have these excitations, or if you want to create these excitations, you really have to create monopoles out of the spin ice that have a higher energy cost, and then you follow this route along the arrows or opposite to them. So in some, these excitations are metastable and they are long lived, and the extreme limit is that when they their lifetime is infinite, what happens is that they lead to additional contributions in the spin-spin correlation functions, and one can plot some of these contributions. Here the contribution is plotted for two such the crystal field excitations, and the spin-spin correlation functions in real space gets affected, albeit by the subleading order. Okay, but moving to the other side, where this term is negative but small, what one finds is that these low energy excitations are now plus minus half in a sea of plus minus 3 half for the ice. And one can draw similar pictures, and here the lowest energy excitations are these a loop of 6 delta excitations, and this loop of 6 delta excitations, just a bit more complicated than the picture that I showed before, still they cannot decay except via monopoles, so they are also metastable. So one of the things that we recently worked out in this preprint is that because of this metastable excitations, if you look at the thermal quench in these systems, because these excitations are present, the spin autocorrelation functions as a function of global time shows this very stretched out plateau. So they basically the spins undergo a thermal dynamical arrest because of these metastable states. One can go into details of how this occurs. What happens is that you start with a high temperature configuration with lots of monopoles and these delta excitations, and then there is, after an initial decay of order 1 time, what happens is that essentially these monopoles and these delta excitations basically stop decaying into each other because of this long energy, this high energy barrier. And in fact, one can show that one can find out the particular kind of metastable states that are formed, the configurations that are formed, which are composites of these the monopoles and the delta excitations of a particular kind. In the interest of time, let me tell you about particularly interesting new result that we found, which is trying to put this spin 3/2 ice in a magnetic field, where this was an old Hamiltonian and I have put it in a Zeeman field, and I'll now consider 2 particular directions of the magnetic field and tell you about the outcomes. Okay, so let's first consider an the magnetic field in the 100 direction, in a certain parameter regime. What happens is that if you look at the specific heat of the system, it shows this very asymmetric peak. The specific heat almost remains 0 all the way up to this energy scale, and then there is a sharp jump, but there is scaling on the other side. So this asymmetric behavior I'll explain to you in a moment. And at the same time, what you see is basically the magnetization has a value, and then it's increases as a function of temperature, and on increasing further it decreases ultimately. Okay, so what is happening here is that this is a 100 field, and for this parameter regime I have a spin 1/2 ice, but once you increase the field, what happens is that some of these spin 1/2 converts to spin 3/2, and that's how they can gain in energy from the Zeeman turn. But because they have to satisfy the ice constraint, you cannot just flip one spin, so you really flip a whole string of spins along the 100 direction, and this proliferation of these strings drives this transition. So as you can see that the number of spin 3/2, which is this middle plot, goes up at the same time and as this transition. So these kind of transitions are, one can argue even on the basis of the free energy, that there are such transitions mediated by strings, and the anisotropy comes from the fact that there is almost no fluctuations on one side, and there are thermal fluctuations on the other side, and these transitions driven by strings have been studied in context of diamond models, and they go under the name of Castelline transition. Sorry for the typo. And this is an example of a 3D Castelline transition, and sort of inverse in the sense that the magnetization increases as a function of temperature initially during this part. Okay. So let me end with even more rich part along the one direction, which is this direction. So let me just point out that if you look at the pyroclo lattice from the 111 direction, it is alternate layers of triangles, which are these green dots. and alternate in between the two triangular layers there is a Kagome layer. Okay, so this plane of black dots is a Kagome plane, and so as I go along the 1 1 1 direction, it's triangle, Kagome, and so forth. Okay, so this is the direction that I'll now think about, and what happens is that as you turn on a magnetic field in this direction, this is the same picture just rotated for to fit in the slide. So to gain so as you increase the magnetic field, suppose you're sitting here, what happens is that all the triangular planes have spin 3/2, so essentially they are more or less dead. They are pinned by the Zeeman term. On the other hand, the Kagome planes initially have slightly more life in them. So initially they are of course pinned to this -1/2, but as you increase temperature, the dynamics starts, they undergo fluctuations and they can mediate transitions. But the way that they mediate transitions depends upon which regime of magnetic field you are in, and let me try to take you through this, which seems to be an interesting effect that we have found. Okay, so let's try to think about staying just in this yellow region but not up here, and think about increasing the temperature. Okay. So what happens is that as I said, that there are these Kagome triangle layers as I go along the 1 1 1 direction, and what at some point when you increase the energy, you increase the temperature in these systems, you start proliferating strings of spin 1/2 in this background along the 1 1 1 direction. So you have this, you flip this spin 3/2 to 1/2, you compensate it by flipping it this -1/2 to 1/2 again to maintain all the ice constraint, 2 in 2 out rules. But now the strings are proliferating in the 1 1 1 direction. Yes. Okay. Yeah. So what happens is that again one can think about the free energy content, and one can conclude that there is a similar transition, Castelline transition driven by these strings along the 1 1 1 direction, and this is the numerical evidence of these transitions for various fields, and we observe the right scaling that you expect from such proliferation of strings. Okay, but let's now go up, crank up the magnetic field even further and try to think about this larger magnetic field region, still starting with this frozen the 3 1 bar 1 bar 1 bar state. Okay. So now what happens is that because you are in a large magnetic field, you don't want to flip this triangular lattice triangle layers, and they remain pinned to this 3/2 value pointing along the magnetic field. Okay. Instead, what you do is that you start proliferating loops. Sorry for these bad cartoons. We are trying to summarize this as I speak. So what happens is that you start proliferating in the Kagome layers the loops which keep intact the ice constraint, but now these loops are made out of plus minus the 1/2 and 3/2 as well as -1/2. So in essence, individual Kagome layers becomes decoupled because the triangle layers are frozen, and you can proliferate these loops independently in all the Kagome layers. But now from the free energy argument, you can show that this free energy does not lead to a crossover, because you can think about one Kagome plane, and you can convince yourself that if you think about a loop of radius r, while the energy goes as linear of r, the entropy goes as the area of the Kagome plane divided by r square. So it does does not lead to a transition, but instead a crossover, which is driven by these loops arising in individual Kagome planes. So what happens is that this Castelline transition, as you go along this line, the changes over to a crossover via critical endpoint, and this is fairly interesting in the sense that I have this string driven transitions, the Castelline transitions, which is sort of midway between a first order and a second order transition, and it ends at a critical endpoint where the loops in the Kagome plane and the loops perpendicular to the Kagome plane have the same fugacity, and right now we are trying to understand the fate of this critical endpoint and various other details. Okay, so with that, let me stop. There should be a summary slide which is not showing up, but I guess this is fine. So what I have told you is that these higher spin representations of pyrochlorolattice might have more interesting physics in them. In particular, I have pointed out this because of this new excitation scale, the slow dynamics can emerge in thermal quenches even in absence of quench disorder, and then there are interesting phase transitions in magnetic field, particularly the 111 magnetic field, and there are certain interesting things when you turn on quantum dynamics of these spin 3/2, which I'll be happy to talk about after the talk. Thank you. Yeah.
In addition to the quantum endpoint,
yeah.
do you also not have a tricritical behavior here because of competing dipolar and quadrupolar order parameters?
So I could turn on the quadrupolar terms because this is a spin 3/2. So it turns out that it even before this tricritical point, it goes to a different Coulomb phase, okay, which is driven by quadrupolar fluctuations. Okay, so that is all a different ball game.
The earlier part of the model was the Bloom-Capell model, actually, which showed tricritical behavior.
Yeah. So, but this is a frustrated version of the same thing.
Without the frustration, I was asking.
So without the frustration, it is this Bloom-Capell model, but with the frustration, the ordered phases are gone completely. So it's replaced by a Coulomb phase. Yeah.
And when you talk about quantum dynamics,
yeah.
do you also include the heat bath effect directly?
Oh, no, I'm thinking about unitary dynamics putting spin flip terms S plus S minus. Yeah.
Yeah. So, okay, without mic, I'm fine.
Yeah.
So
I can hear.
Thank you very much for this complicated talk presentation.
It would be good if you speak into the mic so that the audience also can hear your question.
Okay, so okay, I'm a simple experimentalist, yeah?
Yeah.
So as far as the experiment is concerned, right, for your I equals to 3/2 spins, what to look for?
Yeah, as I said that one of the materials is this, typically the terbium compounds have a low crystal field.
Yes.
So terbium titanate, terbium stannate, these are, so if you look at the spinice literature, these, the terbium family has been sort of dubbed as spinice, but their experimental data never quite fitted into the regular spinice theory, okay? So those are the series of materials that seems to be the first step to look at.
So what kind of experiments you are proposing?
Yeah, so for example, look at the, so there are already experiments, for example, the, so these two, so again, going into some of the details, terbium turns out to be what is called a non-Kramer's ion. Okay, so there is a particular phonon that leads to hybridization of these two, the two doublets, and that leads to extra lifetime. That leads to a shorter lifetime of these doublet modes, which have already been seen in Raman. So that's the first step that tells us that there is a hybridization and of these modes, but we need to try and understand the low energy neutron scattering more carefully, keeping this next doublet, which I think is not, which is only being recently done.
Can we just take a look at the background in case there are someone else? Because we have room for about 1.5 questions. Yeah.
Excuse me. Hi.
Yeah.
Yeah. So I have a question. I just want to know the Hamiltonian.
Yeah.
You talked about monopole, right?
Yeah.
Monopole.
Yeah.
I
Yeah.
just
Yeah.
wanted to know.
This Ising model. Okay. Yeah. So just this term. That's the Hamiltonian that would give monopoles.
But one more question.
Yeah.
So what numerical method did you use for getting these results?
These are various sophisticated versions of classical Monte Carlo, waiting time Monte Carlos and loop update Monte Carlos of various kinds. Yeah. Should ask this person, Hush.
Thank you for the nice talk. So on the same slide,
Yeah.
we discussed that the transition is happening at the same temperature.
Yeah.
But if we just move slightly along it, for instance, the magnetization also saturates at the highest value, and it also matches along the lowest value of specific heat.
Say that again.
So let's say if we
This feature.
yeah, this feature.
Yeah,
do
so
we
there
know-
are crossovers of various kinds coming from the interplay of all these three energy scales. So these are all crossovers of various kinds. Hush might be able to tell you more details about these crossovers.
I think we should move on because we are on time and want to maintain that.
Okay,
Thank you.
thank you.